Okay, so let us continue with this requirement, a set of requirements we are talking about regarding specifying exact bit widths, and we argue that it is it's essential. Let us move on to some other elementary requirements for HDLs. The idea of dividing a design into smaller modules and connecting those modules up in some way is an elementary requirement in hardware design and therefore its specification. So, I should be able to create a module. These terms that I have picked up here, module and so on, these are somewhat generic terms, they are not language specific really. What is the first thing that comes to mind when I design a module? What is the external interface of that module? External interface is essentially defined through a set of ports here. What we have here is a set of input ports and a set of output ports, maybe a bidirectional port if there is one. What are the set of ports I should be able to define in the module? That constitutes at an elementary level the external interface of the module. What other things might be basic requirements? Some electrical characteristics like current levels and so on are optionally relevant here. That does depend, some of this depends on the kind of technology that your system, electronic system is based on, but the idea of tri-stating something is nowadays considered as sort of an elementary requirement. So, a language might provide some way of specifying that a particular output of a buffer is tri-stated, say. As you know, that helps in designing certain kinds of electronic systems. Sensitivity to a clock edge is an elementary requirement in the specification of a digital system. You would like to say on the rising edge of a clock certain thing is triggered, right. So, that is a sensitivity, rising edge or the falling edge, that is a requirement. So, let us include that also among the elementary requirements in HDLs. I could list a number of these, but one orthogonal requirement is what about some programming constructs like file IO or string processing and so on. Is that useful? It is. Why is it useful? Remember, it may not be directly useful in specifying our design itself, right, but there may be other uses of this file IO which you can argue it is useful for design or not, but certainly from an overall design environment it is essential because it is useful in debugging and so on. While the simulation is going on, I may want to print out something. So, some such constructs, file IO related constructs, string processing related constructs are usually included in HDLs, right, even though they are not necessarily relevant for specification of the design itself. Design is not the only thing that we are doing, we are also doing lots of other things. We are generating inputs for testing, right. That is not part of the design if you are generating inputs for testing, but how do you generate that input? It is considered so basic that the design language itself provides some mechanism for you to be able to specify the input itself. Or equivalently, if you just extend that, you should be able to specify your input in a file, and in your SDL you read that file and provide that as an input to the design, right. So, those things are part of an overall design environment, and modern HDLs do provide some mechanisms for that. Okay, so these are some simple requirements. Let us move on to a specific HDL and illustrate a number of these features in the context of VHDL. Yeah.
Where do we use some current levels in HDL?
Where do we use current levels in the HDLs? We will point out examples in the VHDL context where I am able to specify the strength of a signal, that is indirectly specifying the current level. It is useful in various contexts, as you know. It is represented differently in different languages, but in VHDL how do we do that, we will get to, so just hold on for that. Okay. So, this VHDL is a recursively defined acronym. That V is an acronym by itself, it stands for very high speed IC. This language was originally meant for simulation and documentation and so on. When you deliver a design, there is the need for a formal documentation, and there was a specification language, and that is what it started off as. That syntax is based on an earlier generation of programming languages called Pascal and Ada. Interestingly, at that point nobody was thinking that this specification in a language like VHDL or other languages like Verilog are necessarily meant as a starting point of a design. It is more like an afterthought to formally specify what the design is doing after you have designed it. That is how it started off. Now the methodology is different, but you have built a design out of whatever schematic editors and so on, and now you want to capture it so that it could be simulated. Somebody who is buying the product can simulate it in his environment, but nobody was thinking that this could actually be treated as the design itself, and we start our design methodology, our design process from the language. But this is from long ago when the language was first designed. Since then, people found value in just treating that itself as the entry point for the design. The syntax is slightly different. For the Verilog, the syntax is sort of based on C. The third language I have put up there is System C. It is based on C++, positioned as a system level language. So, we talked about what that system level of abstraction was. It is the level of abstraction that captures a design intent before you have necessarily made up your implementation decisions of whether something will be done in hardware or in software and so on. But hardware constructs of the kind that we look for in SDLs are also present in System C. Okay. The question of which one to use is sort of unclear. It is not very important. We will try to, in this course, point out things that are of generic importance in HDLs. We will use a specific example of a language, but that is just an example. Most of the ideas, important ideas, span the multiple languages. They are present in all the languages. Okay. So, of course, learning one language eases the learning of the other, and most of the differences are sort of minor and only syntactic variations. Not all, but most of them are common. As far as tool support is concerned, they are equally good for both VHDL and Verilog. System C, like I said, is used more in system level modeling. It does provide support for a lot of the hardware constructs that we talk about also, but it is not necessarily particularly useful additionally. Over the number of features that are there for hardware description might not be too much more than what is already there in HDLs anyway. That is why while it is a popular language for modeling systems at a little higher level of abstraction, the advantages are not necessarily there if you are going to describe a plain digital hardware system with it. Okay. So, with that, let us move to some discussion about VHDL. At a high level, there is an entity architecture pair in a language like VHDL. That entity essentially represents an external interface of the design. We talked about the requirement for an SDL to support specification of modules and their interfaces. So, that is what this is. Entity is the external interface. The architecture is what captures the functionality, right. How the design works is what is captured in the architecture part. The entity part just has the external interface. If you were to use that module, what is visible to you, how you would connect your signals to this module, that is the information that is there in the entity. It is the architecture that contains the implementation of that module. Okay. So, let us just move on to the specification through some examples. I have used a little low level of abstraction, small gates, in order to illustrate these concepts. That is not to say that you can only describe small gates using these languages. You can very well describe very complex designs. So, but this is there just to illustrate some of the basic syntactical aspects. Okay. So, I have a gate level design, an AND gate here that I would like to model. What is the external interface? So, even before I specify the functionality, I need to specify the external interface. What is the external interface of an AND gate? I have two input bits. So, it is like single bit inputs. This is a 2 input AND gate, and there is one output. That is all that is the external interface, and that I need to capture that in an entity specification. So, I create a list of ports. So, each of these the A, B, C each is a port of the entity, and a port list is specified, that is all that is there in the entity. Okay. So, that this here is a name that we have given to the model, right. We can choose whatever name it is. What you see in green here are all the keywords of the language. So, entity means something, is needs to be there, it is part of the syntax, the port means something, and you conclude this port list with an end statement, and that name there has to match the name of the entity. This is the elementary syntactic requirement. Okay. Look at the port list. I have a list of port specifications, right, something for A, something for B, and something for Y. What information are we giving? Along with A, which is a name that we have chosen, I have two other things. One is the direction, saying it is an input port. The other is the type, right. I am saying that this is a bit type. So, this is a 2 input gate, and each input is 1 bit wide. So, that needs to be specified. If it is a more complex like an integer, I need to specify that it is an integer. The output similarly is captured with that out keyword. I say that is the direction, and that bit type is the output. That is all that is there as an external interface of the AND gate. Remember, we did not yet say what it is doing, we are just saying that this is the external interface. Yeah.
So, that AND gate, the model name.
Yeah. Oh, so what you see in white here, right, the model name, this is our choice. That only what is there in green is predefined. This is part of the language syntax. We could have chosen anything else. We could have instead of ABY, we could have chosen any other names. Instead of the AND gate, we could have given something else. The colons and semicolons are part of the language. Yeah. Any question regarding the external interface? This is simple enough, right? Of course, I can specify any number of ports as necessary, and while these are the elementary bit types, I can have other types for specification. Okay, let us move on to the other part, the architecture part of the design. That is where we specify what it is doing, remember, so or how it works. So, the architecture is a keyword, that is where I specify the functionality. The AND gate here tells us that this is the connection between the entity specification and the architecture. Which entity are we specifying the implementation of? That connection is established by using that gate, using that name that we gave to the entity. This is a name of the architecture. We are saying we have chosen a name called data flow here, does not really matter, you can choose a name of your choice. If it is descriptive in some ways, it is good, but the language provides a way for you to specify multiple architectures for the same entity. Why would that be useful? You could put it to many different uses, but you could, for example, capture different levels of detail of that same design. As time progresses, maybe you start off with a very approximate design, it just represents maybe a very high level algorithmic description, timing is not there, and so on, right. It is still useful to model, like we said, at a high level of abstraction, but later on you may choose to go for a more detailed implementation that could be captured in a different architecture of the same entity. The entity is not changing, the external interface is not changing, only the implementation is changing. So, this could be a way for us to capture different implementations of the same module. Ultimately, when we take it up later for simulation or synthesis or something, we have to indicate which architecture, which implementation we would like to implement, we would like to synthesize or we would like to simulate at this stage, but the language provides us the ability to specify different implementations. That would be by specification of different architectures. Yeah.
Data flow is the name of the.
It is the name that we have given. Why we have chosen this, maybe we will get to later, but you could choose something else.
So, for example, if we have to define multiple architectures for AND gate, so we can give them.
We give them different names.
And when we have to use them, we will specify the entity name.
We specify, yeah, when we use it, we specify both the name of the entity and the architecture of the entity. Yeah.
During instantiation itself?
During instantiation, but we may be running ahead because yeah, that is a use, an example of a use of the entities. Okay, so that is just the interface. specification. We did not exactly explain that functionality there. Functionality is captured in that one statement, but that is what we are coming to. Let us start with the specification of the functionality. At an elementary level, the feature that one would use to specify functionality is what is called a signal assignment. Okay, we will define what the signal is, but as of now we have an entity. This is a full ladder structure which has what inputs? It has 3 inputs. There is A, B are the data inputs, Ci is a carry input, and Si is the sum, and Co is the carry out. So, 3 inputs and 2 outputs from the ladder. I did not show the entity here, but you can easily see how you would represent the entity from that structural information. Okay. So, full ladder is the name of the entity, that is the name of the architecture, data flow is the name of the architecture we have chosen, and between the begin and end of the architecture we have to specify the functionality. Okay, all the functionality has to go there. What is our functionality? I am saying that the sum Si is assigned the value of Ai XOR Bi XOR Ci. This is the standard specification of the functionality of the sum bit of a full ladder. That operator there is the signal assignment operator. There is a CO which is the carry out. Carry out has different logic, it has the AB plus BC plus CA logic. So, that is what is captured in that other statement. So, I have 2 signal assignment statements. What is important to note here, which is a language specific feature, is that these are concurrent signal assignment. Concurrent means that the order in which you specify them is not important, both of them are active at the same time. Okay, so, I need to little carefully understand what do you mean by both the statements are active at the same time. To answer that, we have to answer this question of when is a signal assignment triggered or executed. Okay, you have written a bunch of signal assignments here, that is the specification of the functionality of the full ladder. The rule is the assignment is executed when any signal on the right hand side of that assignment changes, right. I have that expression there. That expression consists of these ports. As of now they are AI, BI, CI, all are ports. SI is also a port, but these are the input ports, right, AI, BI and CI. So, the rule is that that assignment is triggered, that particular assignment statement is triggered, possibly resulting in a new value to SI if you have changes in AI or BI or CI. If any of those signals changes, then the output is evaluated afresh. Now, remember that may or may not lead to a change in the output, that depends on what is the logic that you have given, but the expression is evaluated once more, that is the rule. And of course, if that second statement is also a function of AI, BI and CI, right. So, if any one of those 3 input signals changes, both in this example here, both the statements would be evaluated. Any basic questions on the rule? The rule is simple. Is it intuitive? Does it make sense to have this rule? Conversely, what it means is that if those signals did not change, if any of those 3 signals did not change, then the evaluation of SI would not happen. Would not happen means it somehow retains the old value that was computed. Yeah.
So, but that does not mean that the signal assignment of SI and CO has to be concurrent, isn't it?
By concurrent, we will define in a little closer detail what exactly it means. We are saying that these are independent of each other, right. In this particular case, both are a function of the same 3 variables. There may be functions of other variables, of course. If they are, then the triggering of the first statement is independent of the triggering of the second statement. But does it make sense to have a rule like this? The consequence of this is that if they did not change, if those inputs did not change, then we will not re-evaluate the output. Not re-evaluate means the output retains whatever was the last computed value for the output. Does that make sense? Why does it make sense? No, function, but is it correct first of all according to the way we think about the hardware design? It is correct. In CMOS logic it is correct. right. There is a dependence there on what technology you are using, may or may not, depending on what kind of gates, what kind of transistors you are using, but that logic family works in a way that if the input is not changing, then the output is maintained, right. If that were not the case, then this would not be the rule, it would be something else. But otherwise the rule makes sense. That is what is the, if you have a number of signal assignment statements, all of them are subject to the same rule, which is right hand side and left hand side should be clear from this. On left hand side we have the signal that is being assigned, here it is the port that is being assigned. On the right hand side I have all the signals that it is a function of. So, it intuitively makes sense that if anything changes, then the output may change. Okay. Concurrent signal assignment also means that the execution order is independent of the specification order. So, I wrote these two statements here, first this and then this. If I had instead interchanged order of the two statements, right, that would still be an equivalent design. That is the rule of the concurrent signal assignment. Concurrency means that they are decoupled. There is an elementary rule that is followed for every statement, but each is treated independently, and no particular importance is given to the order in which we are writing these statements. Okay. This is as opposed to a sequential programming language, in which if you have one statement and you have another statement, particularly if there is a dependency between those two statements, then the order is important. If you interchange the order, you may get a different result. Okay. But here, if you interchange the order of specification, then you will not get a different result. How do you establish that, we will get to, but this is the rule of the language. A simulator that simulates your design has to obey that rule. And of course, we as designers need to know that rule also.
If we are writing a sequential algorithm?
We will get to how to write sequential algorithms. As of now, this is only a matter of concurrent signal assignment specification. There I do not have the choice. I need some other construct within the language to actually specify a sequential algorithm. Yeah. Okay. This is good enough to model any combinational logic, right. So, combinational logic in general, I have a bunch of inputs, a bunch of outputs, and how do I specify that? I need to model this combinational logic. There should be an easy way for me. Basically, I have one statement for every output, right. For this output, I have a different statement. Each output results in a different statement. In here I would capture on the right hand side whatever function it is of the inputs. Of course, ultimately it is a function of all the inputs, all the outputs are functions of the inputs. So, what that respective function is, I would capture on the right hand side of the signal assignments, and on the left hand side I would just have the output ports here. Hopefully this is obvious. There is one simplification we may need to perform, which is that I have a system in which there is one input and I have multiple outputs, but the logic may be complex, right. So, it may be a very complicated functionality, and not just complex, in fact the computation for y and z might actually have some elements that are common, right. That is what we have represented here. It is some function of f. So, I have a function of f is a function of x, and g and h are two different functions, but that f part is common between both y and z. So, when that happens, if I restrict myself to having just this syntax of independently specified concurrent signal assignments, then you see that I have to repeat that f part of it, the common part of it, in both the statements, right. That is the only way. To get around that, what I will need is a way to specify first that this is the common computation, and let us say I create an intermediate signal object called t, and then y and z can then be specified in terms of that common object. So, that would be a way for me to avoid the duplication of the f that comes in both the expressions. If that expression is complex, then it makes sense to do this. Okay, so that is the introduction of a signal. This is a new syntactical structure beyond the ports that are there. So, you see that signal corresponds to something that is internal to the module, ports correspond to the external interfaces. Okay. So, this signal is useful only for the internal computation, the outside world does not get to see the T at all. That is how we would like to structure this. Syntactically, here is what we would do. This on the left is the original entity and the architecture specification, and you see that there is one part of it that is common, that I1 and I2 and I3, that is common to both these statements. Right. So, if that expression is complex, then the argument is that we should not need to specify it twice. What I will do is we will take that common expression out and we create a new assignment statement. Now, there are 3 assignment statements, 3 concurrent signal assignments in our design. I create a new signal called temp of the same type, that is also a bit type. That intermediate computation is assigned to temp, and the temp now features in that other 2 expressions. You can see that this is a standard way of simplifying the overall complexity of the specifications. This should be nothing new, we do it all the time in programming languages. Of course, when there is a common computation, we take it out and form some other structure with it and use the result in different places. That is the same thing here. Remember that the temp was supposed to be an internal signal, internal object to this module and should not be visible outside. That is accomplished through declaring that temp as a signal here within the architecture. So, the external world only sees the entity, does not see what is outside. So, it does not get to see temp at all, we get to see temp inside. Yeah.
So, it is written represent intermediate wires oblique storage. So,
yeah.
what does that mean, intermediate wire?
Okay, as of now this is just the functionality, but of course, later on I would need to implement this functionality in some design. What would it translate to if I have a temporary signal that I have assigned? Of course, what the ports correspond to in our real design, once it is there, should be clear. They just represent the external interface, they are pins of the design. But if I have an intermediate signal like that, what would that correspond to? As we talk about the specification of the hardware, it is a good idea, since we are already familiar with the hardware design, what would the corresponding design be, right? Okay. So, now if I say that this is a temp signal, so every construct that we have here, we should be thinking about what is the equivalent hardware. Remember, that is the whole synthesis process, that I should be able to take from this language syntactical specification and generate for you the design. So, you better have an idea even before we talk about synthesis, what to expect from a hardware specification like this. Okay. So, this temp should result in what kind of hardware? It could be storage, it could be just a wire, it could be just an interconnection. That does depend on what you are doing with it, and you would infer some storage if it is really essential. If it is not essential, then it could just be a wire and so on. This is specification of pure combinational logic. Even this too is combinational logic, right, because both are combinational functions ultimately, which means that ultimately they would be either gates or wires. You do not need any storage in the design. So, this intermediate signal, can you imagine what the hardware would be for this structure here? This is just a 3 input AND gate, right. The functionality part of it is a 3 input AND gate, and the output of that AND gate. So, our design would be I1 and I2 and I3, that is my temp. What else do I have here? The temp actually leads to 2 different gates here. One is an XOR gate, where the second input is I2. That means I take it from here, and the output is O1. What else am I doing here? I have an OR gate whose output is O2, and that also takes temp. And the other input here is by 4. That is the combinational logic. It should be obvious. As of now, the implementation is obvious. So, hopefully, we get to more complex specifications of SDL where the implementation is not obvious. That is when it makes to introduce synthesis and automation and so on, but this for the small example it should be clear. And what we have here is that this specification of temp, if you see all the other connections here, all the other wires that I have in fact are part of the external interface of the design, right. The gates are of course internal, but other than that the all other wires or all other pins, these wires directly lead to the pins and they are part of the external interface of the design. So, it is just this that is internal, and that is inferred from our internal signal that we had in the architecture specification. Okay.
Sir, are HDL compilers intelligent to overcome user mistakes and find temporary signals on their own, if in case user has or somebody designer has not?
Are HDL compilers smart enough to infer mistakes of the user of the kind that the temp was not declared and suggest that there should be a temp signal? You used temp, but you did not declare it.
No, what I meant was in the RTL, sorry, the SDL on left and right
Yeah.
can be interpreted in two different ways when you actually put a structural net list. You
Right.
can duplicate the two AND operations there and create 3 input AND gates. But
yes. So, I have some redundancy in the original specification that I have manually optimized in my in that second specification. Your question is, are the synthesis tools smart enough to see that themselves instead of asking us to manually identify that something is common? Here it was obvious, sometimes it might not be that obvious. Remember, you might have specified it in some another set of operations, it might still be a 3 input AND gate, right. Are the synthesis tools clever enough to detect that themselves? They absolutely are. Yeah. Of course, there is a limit to that smartness, but that is indeed the topic of the later stage, the logic synthesis when we study. The idea is absolutely to optimize the logic that is generated. There is a straightforward logic that can be inferred from the way the user wrote the code, but that is only the starting point. The whole point of logic synthesis and all the synthesis and optimizations is that you generate the output that is an optimized net list that need not have any structural resemblance to what was specified by the user. Okay. It should have a functional equivalence, but it need not have a structural resemblance. Yeah. A simple redundancy like this would absolutely be identified by a modern synthesis tool. Okay. The rules are still the same with respect to triggering and execution, even if I have signals here as opposed to ports. So, I had ports here earlier, right. So, these two signal assignments were to output ports, but now I have a signal assignment to a signal. So, actually they are all called signal assignments. The way to understand this is that they are all signals. Ports are also thought of as a special kind of signals, but in general they are all signals, and this rule that we are talking about for triggering and execution of the concurrent assignment statements apply to signals in general, and therefore to also to ports in particular. Okay, so this one would now be executed when I1 or I2 or I3, any of them change. Now we have restructured the specification though, which means that now first of all there are 3 statements instead of 2, but also these 2 statements would now have a different rule for triggering or for execution, right, because the earlier I said that O1, which was a function of I1, I2, I3 would be triggered if any of those changes. Now we are saying that O1 would be triggered only if I2 changes, but also if temp changes. So, somehow there is some difference now in the sequence of the triggering and the execution. So, there is a difference, but is it still equivalent, you think? equivalent with respect to the functionality with respect to the output, it should be equivalent. Yeah. So, it is just that I1 no longer triggers O1 and O2 directly, which it did. Now, it triggers only temp, but that is all right, because the changes, any changes in I1 are captured first in temp, and if temp did not change as a result of I1 changing, did something go wrong? These expressions for O1 and O2 would not be triggered because temp did not change. That is the rule, which is okay, right, because that expression, sub expression did not change, and therefore, the whole expression also will not change, right. So,
temp has a variable relation such that two of them are changing, but the output is not changing. I1 and I2 and I3. Suppose if I2, I3 both of them change.
oh, the rule is if any of them changes, then that statement is executed, which means if two of them change, it would also be executed. All three change, then too it would be executed.
No, then temp will be executing.
Right. That statement would be executing. It may result in a change in value of temp, or it might not result in a change in value.
Finally, the temp value may not be changed in some cases.
Right.
But in the next statement, the compiler assumes that temp is not changed.
Since the value of temp did not change, these other two statements would not even be triggered. These other two assignments would not even be triggered, but we are okay with that, right? It's all right because output doesn't change. The change in input was such that it did not ultimately propagate to the output. That is all. Functionality wise, as you can see, we did nothing. We just restructured the specification in a way that we avoided some things. We simplified the design in some ways. That do you see that there was some common part that was taken out. So, it is in some ways easier to specify. If one were to directly translate that specification into a netlist, then this would lead to a smaller netlist, yeah, because there are some part of the functionality that did not repeat. What is a netlist? Oh, what we have here is an example of a netlist, instantiations of the gates and their interconnections. That is what is called a netlist.
So what is the circuit?
Same thing. Yeah, circuit is the same thing. This is just the terminology that was defined in the first class. It might not be there. Yeah.
Sir, in this case now temp and output 1 are not concurrent in all the cases.
So they are concurrent. These three statements are specified in a way, they are interpreted in a way that they are all concurrent with respect to each other. Now, but what it means is that they are not always executing. Each is executing when its condition is satisfied for execution. That is the meaning of concurrency here. Yeah.
So, but would there be a timing difference between the two implementations that you showed? In one, what
Yeah, so yeah, the timing is an interesting topic, but we will get to that soon. As of now, this is only a functionality distinction, and we are saying there is no distinction. They are equivalent with respect to functionality. We do need to resolve. We have only informally pointed out what the rule is, but it is not obvious how exactly it is going to be applied. So, but that is the topic. So, why don't we just move to the next slide? Modeling of delays is what this question was about. We just need to make sure that our rule is such that if multiple statements are executed and there is a dependency between those statements, say, which it was in that other case, then we should still faithfully capture what the intention was. Okay, let us talk about the delay specification. There are a couple of interesting models of delays that are supported in these HDLs, and both of them let us first informally understand what is the requirement, what is it that we would like as designers, and then also look at it from the point of view of a simulator that reads the HDL and reads statements like that, and make sure that the simulator is able to capture the intent, give us the kind of functionality that we want. The first one is what is called an inertial delay. The idea is to capture transistor related or gate related delay. So, there is a propagation delay that is involved when the input changes in a gate and the output is triggered by the input. That does not happen in 0 time. The statements that we had so far, the outputs were responding in 0 time. I did not say anything about time there, but we do need to specify time, and so that means the element of the delay comes into the picture. So, I say y takes the value of not a, this is just an inverter specification. With couple of other things, I say it is an inertial delay, we will define what that is, and we say that the result shows up on the output port after a certain amount of delay. Okay. So, that 10 nanosecond is the amount of delay, that is what we have specified, nanosecond and after an inertial, these are syntactical constructs of the language. Okay. Actually, the default delay, if you do not specify anything, is actually inertial. So, even if you do not specify inertial, you get a statement like that, that is equivalent to inertial delay. Inertial as opposed to what we will get to later, but that is the requirement. What are we trying to model here? If I say that y is equal to not a after 10 nanosecond, I am trying to model an inverter whose delay is 10 nanosecond. So, that is what I would try to model, which means that this kind of a waveform is what is the implication here. Let us say the waveform for A was like that, that is the input, right, input port, y is the output port. A changes at 0 at time 0. So, what we are showing here is increasing time, and y changes as a result of A changing 10 nanoseconds later. Okay. Then when A changed, the value of A changed again at 12, then another 10 nanoseconds later, I expect the y to get the not A value. Okay. So, that is the requirement. But what happens if at a particular time, at time 30, I have A changing, but A changes back within 5 nanoseconds, that is shorter than the specified delay? What should actually happen? We are trying to model an inverter with a gate delay of 10. Now, it happened that this is more like a spike that is there on the input is changing too fast. What would the real waveform look like on the output when this happens? Of course, you see that this is a digital waveform, this is obviously approximating what the real waveform would be, but in reality you would have that because the input changed from 1 to from 0 to 1, the output would start falling, right, and at time 5 what has happened? It has not fallen all the way down to the level to logic level that we would recognize as logic 0. So, we are somewhere here in the middle, but A goes down to 0. So, what should actually happen on the output? It should start rising back to this. This is what would happen in a more detailed simulation if you were to do a transistor simulation, but at this level of abstraction, the way we are capturing this is that pulse, that spike would be ignored. So, nothing happens on the output, that is how the inertial delay works. It is an approximation to what the actual waveform would be, but informally the way we understand this is that there is a delay specification for a function in our model, and if the output is changing too soon, right, before that much time has elapsed, then nothing shows on the output. Right. So, it is not as though it begins to fall and then gets back, because then it is not a purely digital simulation, it is not a 0-1 simulation. Remember, what is the type for y? We declared the type in our design. What? It was a bit type, right. That bit type is forced by the language to carry only 0 and 1 values, right. So, the opportunity for me to show a wave falling and rising in the intermediate levels between 0 and 1 do not exist, at least for that type it does not exist. So, the initial delay specification is that we will completely ignore the change due to the rising. So, this part of it, whatever happened on the input, we will ignore, and we will just recalculate what happens as a result of the new value. So, on the output nothing will show, that is an important specification of a delay type. You might not want this kind of a modeling for all your designs, but a lot of the designs, but particularly this gate delay if you are trying to model, this is considered a reasonable approximation in a bit level simulation. There is the second kind of delay called transport delay that models a slightly different situation. Both of these are there. The designer has to choose the right kind of specification delay modeling, but this is what would be used. Inertial delay would be used if you have transistor related delays or gate related delays in your. So, for combinational circuits, in fact, this is a good way to model the latency of a system.
So, is there any default value for this delay?
Default value is 0. If I did not specify, like in the earlier statements where I did not specify a delay, then you are saying that the output should take the new value after 0 time. But how it is coordinated is something that we will get to, but if you do not specify, then it is a 0 delay specification. There is use of a 0 delay specification also. The use is that like if it is submitted to a synthesis tool, right, you specify the functionality, you submit that functionality to the synthesis tool and you tell the tool, you give me the best circuit. You do not know the delay, right? The delay is known only after the circuit is built. So, you are only specifying the functionality and you did not specify it, you just said 0 delay, but that is treated as an input of the functionality by the synthesis tool and it gives you an output which at that time you know the delay. Initially you actually do not know the delay. So, there are certainly uses of this of the 0 delay specification also. Okay, let us close this discussion now. We will continue with the transport delay later on.